So 6.3, mass, weight, and gravity. So I defined mass initially already, so I'll just remind you of that. So mass is an intrinsic property of an object. Intrinsic property. So we can say that the mass of an object does not change from place to place. Okay, so it's just the quantity of material or the inertia of an object, so it does not change from place to place. We can find the mass of an object by balancing it on a scale. We balance it against a known mass. So if it balances against a known mass, then those two masses are equal. Let's look next at gravity. So gravity is a force. So this is the force that an object experiences from the gravitational field. So gravity is a force an object experiences due to the presence of another mass next to it. So we can say that when two objects of mass m1 and m2, a distance r from each other, they exert forces on each other. They exert equal forces. What I should say is they exert equal forces on each other. So let's put here equal. The force is proportional to the product of the two masses and inversely proportional to the squared distance between them. So we can say that we have two masses m1 and a second mass m2. So the forces are the force of 2 on 1, and this is the force of 1 on 2. And so the distance between them is the center to center distance. Let's call it r. So we are saying that the force of 1 on 2 is equal to the force of 2 on 1, and that's equal to a certain force F, and this force is proportional to the product of the masses. So that force is F. So we're saying that F, the force F, is proportional to the product of the masses and inversely proportional to their squared distance apart. And so we can remove the constant of proportionality by putting in a certain constant. Let's just call it G, and multiply m1, m2 divided by r squared. And we shall say that G is the universal gravitational constant. So G has the value of G is the universal gravitational constant is 6.67 times 10 to negative 11, and this is going to be newtons meter squared kilogram squared. So what G means is that if you have two 1 kilogram masses at 1 meter apart, the force between them is 6.67 times 10 to negative 11. So it's a very tiny force. This force, this quantity G, was measured empirically by Cavendish years ago. So this is an empirical constant. So it's a gravitational force between two 1 kilogram masses separated by 1 meter apart. So this is called Newton's law of universal gravitation. So it's Newton's law of universal gravitation. So now let's apply this. Let's say that we have an object of mass m sitting on the earth, so or falling close to the earth. So suppose we have a small mass m falling close to the earth from a height h. So let's say this is the earth, and this is a small mass falling close to the earth. So this height is h, and this is the radius of the earth. And so we shall say that the gravitational force between the earth and the object, so let's say net force on the object, is equal to the mass of the object times the acceleration of gravity g, where the net force on this object is just the gravitational force between this object and the earth. Okay, so let's say uppercase M is the earth, so we say this is F equals G, uppercase M, lowercase m, radius of earth, plus h squared, like that. And we'll say that since r of the earth is much larger than h, we shall just use re plus h to be equal to r approximately. Okay, to be equal to re. Okay, so we'll just say that the gravitational force is equal to g, mass of the earth, mass of the object times RE squared, and that should be equal to mg. So if you take out the mass of this object that's falling, then we see that the acceleration of gravity on it is equal to g, mass of the earth, radius of the earth squared. So this just tells us that all objects falling on an object or on a planet will fall at the acceleration of gravity on that planet, regardless of the mass of the object. This is what we found out, that all objects fall at the same rate. So to find the acceleration of gravity on a certain object or planet, we just need the gravitational constant g, the mass of the planet, and divide that by the radius of the planet squared. So we can do that for the Earth. Let's find g for Earth. So can you find acceleration of gravity of the Earth? So this will be the mass of the Earth, radius of the Earth squared. So mass of the Earth is about 6 times 10 to the power 27, I think. Let me double check that. 6 times 10 to the power 24, sorry, 24. 6 times 10 to the power 24 kilograms. Radius of the Earth, 6.4 times 10 to the power 6 meters. So you should be able to calculate the acceleration of gravity on the Earth. No, that shouldn't be correct. Remember that we know already what acceleration of gravity is, so you should be getting about 9.8. So approximately the radius of the Earth is actually 6.36, and then the mass of the Earth is 5.98 times 10 to 24. So I approximated it a bit, so that's why we're not getting exactly 9.81. Okay, so this is close enough. The whole point is to show you that the acceleration of gravity can be found this way. The acceleration of gravity g can be found this way. Okay, let's look next at weight. So we just saw that the weight of an object is just a gravitational pull on it. So we can put that down. So the weight of an object is a gravitational pull on it. So weight is a force measured in newtons in the SI system. So weight is a force measured in newtons in the SI system. So we know that the gravitational force on an object, Fg, is given by G m1. So let's say the gravitational force between Earth and a certain object is given by this quantity G, mass of the Earth, mass of the object divided by radius of the Earth squared. And we know that this gravitational force is just equal to the weight of the object, mg. Okay, that's what we saw previously. So we should be able to calculate the weight of an object by just knowing the gravitational force on it. Before we do that, let's look at how we measure weight. So we can say we can measure the weight of an object by using a spring scale. Okay, so we measure the weight of an object by using a spring scale. Okay, so we can So suppose we place the object on a spring like that on the floor. So this is the object. So this object will have a gravitational pull Fg and a push from the spring which pushes it upwards, which is given by F of the spring, like that. Okay, so what you see when you stand on the spring is just going to be your weight. Suppose that you are not accelerating up or down. When you stand on a spring scale, all that you're going to see is your weight, because if there is no acceleration, then we say that the net force is equal to 0. Therefore, the spring force is equal to the gravitational pull, which is equal to mg, and that's just your weight. Okay. Any questions on that? So let's look at what happens when you are in an accelerating system. So we can say that so. What happens when there is acceleration? Okay. So let's consider a person standing on a scale in an elevator that is accelerating upwards. Okay. So we put an elevator like that, container like that. We have a scale, and we have this person standing on the scale as it's accelerating upwards. So let's say we have acceleration A. Okay. So we know the forces on the person. So let's say the force on the person would be equal to weight mg and support force n. And then we have acceleration A going up. So this person is standing on the scale like that. So the net force on this person is equal to the mass times acceleration. So we are saying m is the mass of the person. So the net forces on this person will be n, which is support force, minus the weight mg, and that will be equal to ma. Therefore, n is equal to mg plus ma. So the spring scale is going to show a support force n to this person. When you stand on the spring scale or a scale, you're going to see a support force n equal to mg plus ma. So this means the person feels heavier. Okay, so n is normally equal to mg when there is no acceleration, but with acceleration, n is equal to mg plus ma, so the person is going to feel heavier. We can do the same thing for an elevator going downwards. So the situation is reversed when the elevator goes down, or when the elevator accelerates down with acceleration A. So what we'll do is we'll do the same thing again. So we have this person standing in the elevator. We have the weight mg, support force is n, and the elevator is going down with acceleration A. So we'll say that the net force equals minus ma, and the net force is n minus mg equals minus ma. And n is therefore equal to mg minus ma. So this time, the support force is less, so the person feels lighter when the elevator is accelerating downwards. So we can use this to study something, a condition called weightlessness. So we may ask the question, what is weightlessness? Does weightlessness mean there is no, what does it mean?
The person feels no weight as G is equal to A. He's on space floating.
Person feels no weight, what does that mean?
No gravity.
Does that mean no gravity? Okay, so that would be the question. Does it mean that G is equal to 0? Okay, so let's examine that and see. So we shall use the falling elevator.
They actually use an airplane rate point 757 that goes.
Yeah, that's exactly right. That's what they do. So let's analyze the falling elevator. And it's the same way, it's the same as that Boeing that you refer to, the Boeing 747. They fly it up to a certain point and then let it drop. And so in a way, it's like a falling elevator. You can simulate weightlessness that way. Okay. So let's say that you have a person in an elevator that is falling. So this person is standing in the elevator and it's falling at an acceleration A. We've already seen this scenario, so let me just do it quickly. So N is the support force, mg is the weight, and so we know that the support force N is equal to mg minus ma. Now if elevator is in free fall and acceleration a is equal to g, then we have N equals mg minus mg, which is equal to 0. Okay, so this is the condition for weightlessness. Hold on a second. What did you say?
When it's right, it's ma minus mg.
Yes, so this is the condition for weightlessness. Okay, N is equal to 0. So the condition for weightlessness is that N is equal to 0. It doesn't mean that acceleration of gravity is 0. Okay, so G is not equal to 0. Okay, so maybe the best way to put it is to say that weightlessness does not mean that G is equal to 0. So as a matter of fact, if you are up, even up to 100 kilometers up, your acceleration of gravity is still close to 9.8. So it's not actually 0. Okay, so there is always acceleration of gravity. It goes as 1 over r squared, so it goes all the way out to infinity. Okay, so it's not 0. That's the whole point. So you have weightlessness when N is 0. Okay, so there is no longer support. That's when you start floating, in the elevator. So this person is falling in an elevator. Once, if you were in an elevator in a very tall building and the cord broke, what will happen is to start falling. At some point, if A becomes equal to G, you start floating until you hit the ground. Then back to reality. But that's what happens. So that is the condition for weightlessness. N is equal to 0 because A becomes equal to G. The falling as the acceleration A becomes equal to G. So the point is that this is one of the things that Einstein used to come up with the general theory. This is one of the principles. It's called the principle of equivalence between gravitational and inertial mass. So for example, if you're on a planet, or let's say you're in a spacecraft like this, and it is accelerating upward with an acceleration A equals G, then you are standing there, right? Or if it was falling and A became equal to G or more, then you'll be standing upside down, right? So there's no difference between this condition and if you were standing on a planet like this with acceleration A equals G. That's what is the principle of equivalence. So you cannot tell the difference if you are in a spacecraft where A is equal to G, or if you are standing on this planet where A is equal to G. You see what I'm saying? So that's the principle of equivalence. Well, that's an interesting aside. So that's weightlessness. Let's look at, I guess, maybe we can stop here. Because let's just talk about friction quickly, and then we'll be done with this section. So the next force is friction. I'll use the squiggly F for friction. There are two types of friction. We have the static friction, F subscript S, and dynamic friction, F subscript K, or F. So dynamic friction is the same as kinetic friction, so I'll say F subscript K for that. And of course, friction is a force. So this is the force that opposes motion, meaning that if you are moving to the right and you are in air, then the frictional force is to the left. Or if you are moving to the left, then it will be pointing to the right. So it always opposes your motion, which way you are going. Okay, so friction is a force opposing motion. Let's look at static friction quickly. So static friction, this is the force between objects in contact, or between surfaces in contact. Let's use surfaces in contact instead. So this is the force between surfaces in contact. It depends on the types of surfaces and their areas. Okay, so types of surfaces and their areas. So let's consider an object of mass m on a surface. Okay, so we have this object on this surface. So this surface is rough. If there is no force acting on this object, then there is no static friction. So now if I come in and apply a small force to it, then I'm going to have a tiny static friction Fs, and then I can continue along this line, apply a little bit more force, and I get a little bit more static friction Fs, and this can just go on. I've run out of space there. So the point of this is that the static frictional force between the object and the surface will grow. It will grow to a maximum, and when the applied force, exceeds F or maximum static friction, then the object will start moving. Okay, so what we'll have then is that, suppose we get to a certain point where this is Fa and this is static friction Fs max, then we can say that Fs max is equal to mu Sn, where this is of course mg and that's n. If Fa is greater than Fs max, object slides. Okay, so normally the static frictional force Fx is less than or equal to mu Sn. Okay, so it's so when we put the equality sign, it means we are at the maximum. So Fs max is equal to mu Sn. Okay, where n is equal to mg. Questions on that? And so once the object starts sliding, then we now have kinetic friction. So we can say that once sliding begins, we now have kinetic friction F subscript k. Okay, where F subscript k is equal to mu k n, and F subscript k is a little bit less than the static frictional force, maximum static friction. So I can draw a graph for you. So this is the applied force, and this is your frictional forces. And so the static friction is going to grow until it reaches a maximum. This is Fs max. And then once the object starts sliding, it goes down. So this is Fk.